Welcome to Easy BTech, your guide for BTech and beyond. The today's topic we will discuss about transistor biasing. In the previous session we clearly studied about what is a fixed bias and what is the stability factor for that, and you are having more stability factor for the fixed bias network. That is why its stability is unstable, and the operating point is not stable, and you can get more distortions using a fixed bias circuit. Similarly, if you use self bias, somehow it is somewhat better compared to the fixed bias network. Okay. Now the third type of biasing is we will use a self bias, voltage divider bias, or emitter bias. Okay, we are using this third biasing technique, and we are reducing maximum of noise or maximum distortion free, or a faithful output signal can be produced using this self bias circuit. Okay students, we will start it now. Okay students, we will start. That is self bias or emitter bias or voltage divider bias. Voltage divider bias. So these are the either self bias, emitter bias, voltage divider bias. Okay. Now self bias circuit is used for the minimization of stability factor. Self bias circuit is used for the minimization of stability factor. Next, self bias is used for better distortion free output. Distortion free output signal. Self bias consists of biasing resistors R1 and R2. Self bias stability factor is very low compared to fixed bias and self bias circuit. Fixed bias and base to collector feedback bias. Okay students, now we will see the stock diagram. Okay students, this is a self bias circuit. Self bias circuit using common emitter configuration. Okay, this is an NPN transistor. It is emitter, it is collector, it is base. Okay, this is a circuit. These are the R1 and R2. This R1 and R2 are known as biasing resistance. Biasing resistors. Next, RE. RE is known as emitter resistor, which act as negative feedback, to decrease the collector current, and maintains overall collector current stable. Okay, due to temperature, collector current increases, and due to this negative feedback, the current through the RE is IE. Okay, IE increases and negative feedback, and in such a way that current through the BJT decreases. Both IC current will increase and IC current will decrease. Overall, the current of collector current, that is an output current, which maintains a stable. That is why this voltage divider bias or self bias will have a stability factor. That is why it is widely used. For all the amplifier circuit, we are using only such a type of biasing network. Self bias circuits is widely used. Voltage divider bias is this another name, that is voltage divider bias circuit is widely used for the construction of an amplifier to produce a faithful output or a distortion free output. Is it clear? Now here from this circuit you can remember already we have done in the previous session, that is reactance Xc is equal to 1 by J 2 pi of C. For an DC analysis, frequency is 0. Now you can see here, for DC analysis purpose, what you can say, that is Xc is equal to 1 by J 2 pi of C. As the frequency is 0, then automatically reactance becomes 1 by 0, that is it becomes an infinity. Reactance infinity means it can act as an open circuit. Is it clear? Now all capacitors behaves open circuit for the DC analysis or DC supply. Okay, then the circuit is drawn as this circuit can be drawn as, but neglecting this and this, then we will draw in this manner, that is RC, RE, R2, R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, R11, R12, R13, R14, R15, R16, R17, R18, R19, R20, R21, R22, R23, R24, R25, R26, R27, R28, R29, R30, R31, R32, R33, R34, R35, R36, R37, R38, R39, R40, R41, R42, R43, R44, R45, R46, R47, R48, R49, R50, R51, R52, R53, R54, R55, R56, R57, R58, R59, R60, R61, R62, R63, R64, R65, R66, R67, R68, R69, R70, R71, R72, R73, R74, R75, R76, R77, R78, R79, R80, R81, R82, R83, R84, R85, R86, R87, R88, R89, R90, R91, R92, R93, R94, R95, R96, R97, R98, R99, R100, R101, R102, R103, R104, R105, R106, R107, R108, R109, R110, R111, R112, R113, R114, R115, R116, R117, R118, R119, R120, This is VCC. This base, collector, emitter. This is the circuit. Now the voltage across the base, that is the voltage across the base terminal, we can write what you can write. Now here if you want to write, we can write this circuit as in this manner: voltage across the base terminal, okay, applying the voltage divider rule, means in this supply, and we can find the voltage in between this, that is across this voltage. We can assume this voltage as a VT, Thevenin voltage. Thevenin voltage is equal to applied voltage is VCC into across voltage, that is R2, by total resistance R1 plus R2. Okay, V Thevenin is equal to the voltage across the base terminal is applying the voltage divider rule. The total voltage applied is VCC into voltage across the resistor R2 by total resistance R1 plus R2, that is the voltage across the bias, and the biasing resistance, this RB is equal to R1 parallel to R2. This RB or R Thevenin is equal to R1 parallel to R2. Both are same. This V Thevenin we may use VB also, no problem. Now we can write this, we can modify this diagram. This diagram can be modified as, the voltage here is VB or V Thevenin, and the V Thevenin or VB, and the resistor across the base, that is RB or R Thevenin. Okay. This is RE and this is RC, and the voltage here is VCC, is a loop, and in this current is IB. Okay students, okay, already in the previous we have seen what is the V threshold or V Thevenin's voltage or VB voltage or RB voltage. Okay, this we write V threshold or VB is equal to voltage divider rule function, that is VCC into R2 by R1 plus R2, and RB is nothing but parallel form of R1 parallel to R2. Okay, now this will write this equation, that is VB is equal to, that is IB into RB plus voltage across here to here, this voltage is VBE plus emitter to base, that is base to emitter current, IE into RE. It is equation 1. This we may write as VB is equal to IBRB plus VBE plus IE can be represented as total emitter current is equal to, in the transistor, IB plus IC. IE current is nothing but IB plus IC. That is, you will write this as IB plus IE into RE. Okay, this we will write VB is equal to IBRB plus VBE plus IBRE plus ICRE. Okay, this is equation 2. From this we will write that is, see here, this same expression. From this we will obtain IB. Here IB make common, and you can obtain the IB value. That we will get VB minus VBE is equal to IBRB plus IBRE plus ICRE. The same term you can see here. VB minus VBE is equal to IBRE, IBRE and ICRE. Okay, from this you can write VB minus VBE minus this IC, you can bring this side, ICRE. From this you can make the IB current constant, IB RB plus RE. Bring this side. To get IB, we will get VB minus VBE minus ICRE by RB plus RE. This may also write as VB minus VBE by RB plus RE minus ICRE by RB plus RE. Okay, this is the value of IB. Now from these expressions we got the value of IB. In the loop 2, you can write this expression, loop 2, apply the KVL, you will get VCC is equal to ICRC plus VCE plus IERE. This equation we can write as VCC is equal to ICRC plus VCE plus IERE. This is the equation 3. This you are getting the expression. This is the IB value. Now to find out the stability factor, what is the formula for stability factor? 1 plus beta by 1 minus beta by IB by IC. This is the stability factor. We got the value of IB. Now differentiate this IB with respect to the IC. Differentiate IB with respect to the IC. Now what we will get? This is the IB value. Okay. Now students, you can see here we got IB value as VB minus VBE by RB plus RE minus IC RE by RB plus RE. Now differentiate this IB with respect to the IC. Now this term, differentiation of a constant is 0 minus differentiate of IC with respect to the IC, you will get minus IE by RE by RB plus RE. Okay, this is IC. Okay, you are getting this as an factor. Now you can substitute that value. By substituting that, you will get the stability factor 1 plus beta
by 1 minus beta minus Re by Rb plus Re. Now if it will go that side, we will get the stability factor 1 plus beta by 1 plus beta Re by Rb plus Re. Okay. Now from this expression, stability factor is equal to, now this 1 plus beta you can bring common, 1 plus beta into 1 by this 1 will come this side, Rb plus Re plus beta into Re. Okay, this you can multiple here, and by Rb plus Re, this will go up, Rb plus Re.
This is the value. Now what you can do?
This assume as equation 4. Now from this, make the Re common. From the numerator and denominator, make the Re as a common. Now what you will get? What is the stability factor? Stability factor is equal to 1 plus beta. You will get here Re common. Re, if you make common, you will get 1 plus Rb by Re by, you will get here Re by Re plus Rb by Re plus beta into Re by Re. Now here Re will get cancelled, here Re will get cancelled. Now you will get this value, that is stability factor 1 plus beta into, that is 1 plus Rb by Re 1 plus beta plus this Rb by Re. This is the final stability factor. This is the final stability factor for self bias circuit. Okay students, now we will find, by taking an example, we will find what is the stability factor for that. Okay students, if you see this all, you will get it. This is the circuit for a DC analysis. We may write like this, and voltage divider, we can apply the voltage across the base terminal using a voltage divider rule. Applied voltage by across resistor by total resistor. You will get, and you will get the following, and you will get this stability factor. Okay students, now we will discuss
A small example.